nth term of a Taylor polynomial. Yes? So whatever coefficient is right there, here, let me get my little highlighter. Okay, so whatever coefficient is right there, that means that that was f prime of c. Whatever the value was right there, that means that that was f of c. Yes? What if I just know what that whole thing was equal to? For instance, f double prime of c over 2 factorial, it has to be in front of the squared. Agreed? So here I go and I find the squared, and I see that that was a negative 4. That means that this and this had to have corresponded. So whatever I did and simplified it to here, it had to have started from here and then went and simplified to that guy. Agreed? So if I wanted to find, if I asked you, is there a reason you have your phone? Okay, thank you. So if I asked you what this guy, like if I asked you what is f double prime of 2, then you would have to set those two guys equal and solve for f double prime of 2. Does that make sense? Okay, so if I said that f double prime of 2 over 2 factorial, in this case would equal whatever was with the squared part, which is negative 4. And that's why I kind of set that part there. Now, how do I go solve for this guy? Yeah, we multiply both sides by 2 factorial. So it is f double prime of 2. Close. Negative 8. Is that okay? So just the original and the derivative are pretty simple because there's nothing more to really simplify with them. There's no factorials involved in the equations or anything, right? Okay, but on the next one, if I want to go find now what, choose a different color, if I want to go find what the third derivative is, then I'm going to have to go look and see what's in front of the x cubed. So the x cubed part is here. That is the reduced part. So what does this match with? Sorry. It matches with that guy. Yes? So if I set those two equal, then I can solve for f double prime of the 3. And that's what I did here. I said the third derivative of my 2 over my 3 factorial is equal to that 3. You kind of see where that comes from? So solve for the third derivative. What do we get? 18. Because 3 factorial is the same as 6, right? Very good. Okay, so let's see if you can try it with this AP example. Okay, see if you guys can do this one with your group. I'm having to leave my photo. I'm trying to make it rental. I'll tell you that. No! Yes! It is a new car. And so all of the different lights on the dashboard started like going haywire. And so when that happens, your car goes into quote unquote what's called, mine does because it's a really nice car. It goes into limp mode. And so I couldn't drive it like past 20 miles an hour. And it was like doing this. That was on Monday. I didn't play Christmas today. And so we had to skip the baby showers for all of them at school. And the kids and I drove like this on the highway too. Everybody's like going past us. We're like, don't honk at us. And so we get into the car place, and then they're like reading the diagnostic and they're like, it's not showing anything. We don't know why it's doing it. So they've had it since. So I have a dog's journey right now. Anyway, keep going. And that was recorded. I just realized that. Okay. Hi, Thor. Oh, yes. Okay, how we doing? Okay. So I'm going to show you how I would do it. Where am I centered, by the way? How do you know we're centered at 0, Noah? Yeah, it's just x. There's no like x minus 2 squared, right? So it's just the x. So I know I'm centered at 0. And it says at 0, right? Okay, so I know that's my c. So basically, I can see that f of 0 has to match with that guy. So f of 0 is 3. I know that f prime of 0 has to match with that guy. So that's just -4. Those are the basic ones. Then we get into the little bit tougher ones that say f double prime of 0 over 2 factorial has to match with 2, the one with the squared. So f double prime of 0 is 4. Okay, if you didn't get that far, keep going and get the last one. So again, be careful because they're trying to make you think 3 times -3, 9! But it's not 3, it's 3 factorial, which is actually 6. So 6 times -3 is -18. And my answer is C. No, you can. Okay, you can do that, but it's going to be a little bit more complicated. Okay, but yes, yes you can. That's the creative one. But like I said, there's going to be some instances where the terms get a little bit crazier, and you're not going to want to do that. You'll want to match. Okay. Okay. Here you can see this is now an essential knowledge of recognizing those coefficients. Okay. Okay. So do you remember the second derivative test? It said if we had a critical number, that's when the first derivative is 0. So I have a critical number, the first derivative is 0. If the second derivative then is less than 0, it would mean I'm concave down. So what did that critical number have to be? A relative max. But if I was concave up, then that critical number had to have been a relative min. And that was my second derivative test. And if the second derivative is 0, then we're inconclusive. Okay, so kind of thinking back to this guy right here. We said, what's my first derivative at 2 in this case? Well, did I see an x minus 2 to the first? So what did it have to be? 0. Agreed? What was my second derivative at 2? We found it. We found it to be -8. So by the second derivative test, what was at x equals 2, what happened? It was a critical number, concave down, which means it would have been a relative max. So this is where a relative max would have occurred. And I can see that just by looking at those coefficients. So that's what we're going to look at. See if we can figure this one out. Okay, just by looking at those coefficients with the second derivative test. This says, given the fourth degree Taylor polynomial, this guy right here, and that is for that function. Okay, great, thank you. Okay, we really need to know that piece, but okay. Determine whether f has a relative max, relative min, or neither at x equals 0. Well, are we centered at 0? Okay, that's a good thing, or I wouldn't know anything. Okay, if it asked me at x equals 2, would I be able to tell them anything? No, because we're centered at 0. We only know information at 0. Okay, so at x equals 0, we want to go see what happens. So what two values do I need to know? F prime of 0 and f double prime of 0. Go find those with your buttons. What's f prime of 0 going to equal since I don't see it? There's no just x, right? To the first. So this guy was 0. That's a good start. Lets me know I have a critical number. And we're going to do our whole matching thing that I know f double prime of 0 over 2 factorial has to match with this guy's coefficient. So what is that guy's coefficient? 1 over 4 factorial. Okay, that's weird, but great. We can still do that problem. Does that make sense? Okay. So 2 factorial was just 2. 4 factorial is 24. Are you sure? 2 times 3, 6 times 4. Okay, yeah. Oh my gosh. I just lost it for a second. Okay, so f double prime of 0 is going to equal 2 over 24, which is 1/12. Okay. With those two pieces of information, do I have enough to determine if I have a relative max or relative min? Yes. So we're going to say by the what? Second derivative test. Since f prime of 0 is 0. Okay. Good job, Grant. That was perfectly said. That's not math. Okay, all good? And we already did that one. So you have one more essential question left for 8 seconds. Go fill that in. And then we're going to continue to 8-8. Noah said, set the coefficients equal to f to the nth derivative of c over n factorial and solve for f to the nth derivative of c. So that was pretty good. Matter of fact. Yeah. That's nice. Anybody kind of draw a matching picture? Match these two. That's probably what I would have done. Okay. Got 30 more seconds. Finish that one up. Okay, so we're going to go into 8.8 now. We're going to get through the interval of convergence. So if you kind of see what we're going to do today are these first 3 bullets, and then we'll practice some more of the third one and stuff, and do the fourth one tomorrow. So we'll finish that up. Okay. But what we're going to do is we're going to understand the definition of a power series now. This is not just a series. Power series has x's and n's. So basically, like let's say that I had this 1/2 to the n as n starts at 0 and goes to infinity. This series is going to be what? Let's write it out. 1 plus 1/2 plus 1/4 plus ... right? Now what I'm going to do is I'm going to involve maybe some x's. So see how I have x's and n's? When I just had n's, I was looking at the numerical values. Those numerical values are going to basically be the coefficients in the polynomial. So now what happens is I involve the x. This is 1 plus x over 2 plus x squared over 4 plus ongoing. Yes? So this could have actually been a second-degree Taylor polynomial to approximate something. So the series is allowing me to go out to how many terms? An infinite amount. So that's what this power series is doing. It's allowing me to go out to an infinite amount of terms by writing it as a series. Okay? So once we have the series and we have these infinite amount of terms, we're going to go see what happens. So let's say I have some sine function. And maybe I'm centered right here. If I go out an infinite amount of terms, does that mean that I have to match everywhere? Forever and ever and ever? Is that what we were doing yesterday? We were matching the polynomial to the function, right? Okay. Zach, you okay still? All right. You want to stand up? See if that helps? Okay. So it could match everywhere. So this series here could match the function everywhere. Or even if I went out an infinite amount of terms, I may still, let's say that's where I'm centered, only be able to match for so long, no matter how many terms I went out. Okay? Or, again, for some functions, no matter how many terms I go out, and I'm centered here, that's the only place that they match, just like a tangent, and no other place. So that's what we're going to look at here. Okay, so let's see if this makes sense. We have a power series. So now we're going to see the in part and the x part. So we're going to have the coefficients with the variables now. Because I'm trying to write out this long polynomial. Yes? Okay. I can see where I'm centered just by looking at this x part. If there's no x minus anything, then we are centered at 0. Here I have x minus a negative 1. So I'm centered at negative 1. You kind of see how you can see where you're centered just by looking? Where are you centered here? 1. Okay, so it's always going to be important to know where are we centered around? Where are we starting to try to converge from? And we said 3 things could happen. So again, like let's say that I had this function, and we may only, so this is maybe where I'm centered, we may only converge at that c value. So this is like my x-axis. That's a possibility, no matter how long I went. Okay, we could have something like this. And say, again, here's like my c value on the x-axis, where I'm centered, and we may only converge for a certain amount of time. So maybe we converge from here to here, meaning we have this radius of convergence going on. And that could happen. Okay? Or we could be really, really lucky, and this could be a really awesome power series, and we could match it everywhere. So basically, again, if this is where I was centered, I would match everywhere, okay, for that C. Which means our radius of convergence would be infinity, because I'd go out forever and ever and ever. Those are the 3 things that could happen. Depending on the function. Does that make sense? Is anybody confused about 3 things that could happen with this power series? Okay, Josiah. What is a power series allowing me to find?
The radius of convergence or divergence.
Okay, but what is it? Let's start with, what is a power series? Let's just start there.
The series that's the exact value of the function given itself.
Okay, so you're reading verbatim. What does that mean to you?
I don't know if I've used.
Okay, what did we do yesterday? Let's kind of go back for a second.
Like the K4 and further.
So we went and we found, we graphed that on the calculator, and we had like this e to the negative x, okay? And then we went and we found something and maybe did it like match for a while, and then I don't remember what it did exactly, but it matched for a while. So this original one was my function, right? That was the original function. What was this guy that we matched it with? Well, we went more than a tangent. We actually went to degree 5. And this was our... Yeah, we used it to create, we used all, like, the first through the fifth derivatives to create what? Who can help it? What did we create? Yeah, so this was our polynomial. Okay, and we actually did the 5th degree one here. So we found this polynomial to approximate the function. And we matched for so long. So this only went to the 5th degree here. What does the power series allow us to do? Okay, try to match infinity, but it takes how many, if this was the 5th degree, the series allows it to go to how many degrees? The nth degree, like all the way to infinity. So it didn't just stop at the 5th term here, it kept going x to the 6th, x to the 7th, x to the 8th, all the way to x to the infinity. That's what a power series is letting you do. So it's rewriting this polynomial as a series, so you don't have to write out an infinite number of terms. Because we die. Okay. Yeah. Okay. So, dun, dun, where were we? Okay. So, the power series is what now, Josiah, in your own words? He loves me today.
Polynomial that you can match up in a number of terms.
You match it to what?
The original.
The original function of some sort. Will it match up infinitely, though, even if I took an infinite amount of terms? Will it match infinitely?
Not all the time.
Okay, what are the 3 possibilities that could happen? Don't look.
It can converge, diverge, or equal 0.
What are the 3 possibilities of how it can match? Kellen?
Match.
At a
point.
And what is that point? Your
Center.
center. It could match a what?
A section.
A section? What are we going to call that section? Interval. So we could have an interval of convergence. Or it could match everywhere. Okay. Are we good? Kind of? Feel better a little bit? So, how do we determine where it's going to match? We are going to use this ratio test. So let's review what the ratio test says. It says I take the limit as n goes to infinity of Miss McCaffrey over Mr. Okay, a sub n plus 1 over a sub n. Yes? And I can get out 3 things. I could get that it is greater than 1, which means that I diverge. I could get that I am less than 1, which means that I absolutely converge. Okay. Or I could get that I equal 1 and we have no idea. Okay. And this part right here was a horrible start. Okay. This part right here is going to be a big concept that we're going to get into more because we don't know what happens when it's a 1. Okay, so let's go look at this. It wants me to find the radius of convergence. So let's recall what we saw a little bit ago in our notes, that the x minus c is less than my r. So the c is where I am centered, and when I get it to that format, my r is my radius of convergence. See? See. Okay, so we are going to use the ratio test when we are looking for these intervals of convergence. So we're going to take the limit as n goes to infinity of a sub n plus 1, which would be 2x to the n plus 1, which I'm just going to say that's 2x to the n times 2x to the first, over 2x to the n. So we only did the n plus 1. We didn't do anything with the x's. Okay, so this is going to equal the limit as n goes to infinity of the absolute value, what cancels? 2x to the n, so I'm just left with 2x. Okay, we're going to make a little side note really quick, okay? And then we're going to come back. Tell me what that is. 2. We all don't have a problem with that, right? There were no n's involved. No n's involved, okay? So, it's just that number. Agree? Okay, we are taking n to infinity, but we have no n's. Oh, so it's just 2x. Well, close. We still have to keep the absolute value parts. Is that an okay concept? Okay, so by the ratio test, I know that we would converge absolutely when what? That guy is less than what? Well, you reduced too much, but yes. Just when that guy is less than 1. Okay. We'll get to that next. Okay, so that's what the ratio test says. That when this answer right here is less than 1, we converge. And we need to get it into this setup to find my radius of convergence. So what do I have to get rid of in here? The 2. So can I pull the 2 out of the absolute value? And then take it over, and this is the absolute value of x is less than 1/2. So do we see how that's basically x minus 0 is less than 1/2? So I can see I'm centered. I have that set up. So what is my radius of convergence? That's my answer. Okay, now let's look at this. Let's just get a little side note again for our visual. Let's see what's actually going on here. So I'm going to come here on my x-axis, okay? We said that we are centered at 0, and we had this like radius of convergence going on of 1/2, right? Which means that I would have 1/2 and what's over here then? Negative 1/2. So everywhere in here that I plug in my x values into that absolute value of 2x, what happens? Everywhere in the red. So 2 times 0 is 0. Absolute value is 0. Is 0 less than 1? Bonus. Let's try like 1/4. 2 times 1/4 is 1/2. Absolute value is 1/2. Is that less than 1? Sweet. Let's try over here. Negative, what, 0.49. Okay? Well, let's just say negative 1/4. Make our life easy. Okay. 2 times negative 1/4 is negative 1/2. Absolute value is 1/2. Is that less than 1? Okay, so I can see that all of these guys inside would converge. Now let's pick all these guys on the outside. So like 1. What happens when I plug in 1? Oh, and the absolute value of 2 is 2, which is greater than 1. Diverges. Try something over here. Negative 3/4. Right? What do you get out? 2 times negative 3/4 is negative what? Negative 3/2. Absolute value is 3/2, which is greater than 1. So all of these guys diverge. And that's what we are seeing. What happens, though, right here and right here? Oh, if I plug in 1/2, what do I get out? 1 inconclusive. When I plug in negative 1/2, what do I get out? 1 inconclusive. So IDK, I don't know what's going to happen here at those guys. Okay? We're going to get back to that. But can you see it visually, what's happening as you're picking these X values? Okay. Find the interval of convergence on number 2. Go. State that I'm using my ratio test. Do I even have to worry about that negative 1 to the end as I go plug it in? No, it's always going to be a positive 1 when I do the absolute value. So make your life easy and just don't worry about it, right? You don't have to put it in when you do the absolute value. Okay, see if you got the right limit. Okay with that? Maybe one more time for the limit. You got that? Keep going. Is that okay? Wait one more time for that. Okay, so the radius of convergence isn't too bad. Nice. When they, however, ask me for the interval of convergence, I have to do a little bit more. Just a little bit more. Okay. Okay, so you could use the the root test on this too, you guys. You don't just have to use the ratio. But personally, me, I like to just keep it systematic, and I like using the ratio. Okay, because if the root works, the ratio will work too. I don't know, I think it's easier. That's up to you, okay? So here we've already discussed that endpoints are inconclusive, and we must test separately. And that means I'm going to have to use my flippy flappy on my series. Okay? You guys are already thinking, yes! I was hoping we still got to use those. So we're going to use all those series tests. Okay. Now in 8-9 or 8-10, I forget, but on down the road, we are going to see some that we will use the geometric test. And just so we make a little note so we kind of are understanding, the reason we're testing these guys is because we know they're inconclusive. But if I have a geometric series test, what are the conditions for convergence and divergence of a geometric? This one, the absolute value of r is what? Less than 1, and this is when the absolute value of r is greater than or equal to 1. So do I know what's going to happen at these endpoints? They diverge. Because there's no ambiguity in the geometric. We know converge, diverge. But in ratio, there's ambiguity when it equals 1. That's why we have to test the endpoints. But when we get to geometric, we're going to know, hallelujah, we don't have to test the endpoints. Okay? Just so it's in the back of our mind that we don't always have to test endpoints. But we would have to with the ratio test because they're inconclusive. Okay? All right. This next one says, find the interval of convergence. Well, first we got to get to the radius part. So knock that part out. To rewrite it with my x's in front, it makes it easier for me to find that answer at the end, personally. See if you got it reduced to that. Is everybody there so far? Raise your hand if you want more time. Okay, so again, I'm taking it as n goes to infinity. So as I'm looking at these ends, am I bigger on top, bigger on bottom, or the same? The same. So when they're the same, I take my, what? Coefficients. What's my coefficient of this end? X. What's my coefficient of this end? 1. Okay, so we can say converges when that absolute value of x is less than 1. When are we set up in that x minus c is less than r formula? Yes. Because we're centered at 0 here. And again, I could see I'm centered at 0. Okay, so again, just a little visual so we know what we're doing. We said on this x-axis we are centered at 0, and we're going to go out with a radius of 1. So up to 1 and back to negative 1. We know all of these guys do what? Converge. We know all of this part diverges. But what we don't know is what happens at 1 and -1. So we know the interval, though, is something like this. So I can drop my absolute value bars, bring it on down, but with question marks, if they're included. Are we good so far on that? So this is when it gets really fun. We have to go plug in those x values and then refer back to what we knew from the first part of this sequence and series, okay? So we're going to plug in, and I'll just start with 1 first. Okay, we're going to plug in those 2 endpoints and see what happens. So I'm going to plug in 1 to what's going on up there for x. I gotta see it. So I plug 1 into that x spot. And reduce this for me as much as you can. One to the n is just always what? 1. So I don't even need that part. Maybe one more time to get to there. So we know we're going to try the what? We're going to try the alternating series. Okay. So the first thing I have to do is take the, as n goes to infinity, of just the non-alternating part, which is n plus 1. If it equals 0, does that tell me anything? No. But in this case, it actually equals, oh, what the heck? I don't even have to finish the alternating series because I know that this guy actually diverges by the what? Its term. So I know that on this one, there's no bar. Agreed? It's not equal to. We've got that checked off. So now let's go see what happens at -1. So plug it in and reduce. What does that reduce to? So let's just kind of look at that. -1 to the n plus 1, -1 to the n, right? That's what we're having to think through. So that would be the same as -1 to the 2n plus 1, which is basically -1 to the 2n times -1 to the first. So what does this guy do? It's always going to be what if it's 2n? Yeah, there's no alternating part left. All I have is -1. We tried to practice that a little bit in our pre-series stuff. So this guy is just -1 times n plus 1 when I reduce. Bam, what do I know it does? Diverges by the, yeah. Definitely that limit's going to go not to 0. It's going to go to -infinity, right? So again, I know that that guy's not included. So my overall answer is -1 is less than x is less than 1. If one of them converges, like let's say I had a less than or equal to here, does that mean this one has to converge? No. They're independent, okay? One doesn't affect the other here. So you could have a whole mismatch of things. Okay? We're going to do one more. Try it with your buddies. No, we're just kind of keeping it easy right now. We're getting the concept down, and then we'll start changing that. Okay? Good question. Tell me what test you're using at the beginning, please. did, I think. Okay, and you do the n plus 1. Thank you. Okay, better. Anybody just kind of say this? Or do you need to, if you need to write it out, -1 to the n times -1 to the n. If you can see it, then great. Okay? But it's kind of up to you if you want to write it out and simplify. Unless you're pretty good at it, then I would write it out so you can see it. But a lot of you will just be able to jump to here. What does this guy do? Converges by the p-series. Alright, that's just basically 1 over n squared. Okay? So in this case, they both converged at the endpoints. Okay. Huh? No. The only absolutes are if you take the absolute value and create a new one, right? Or you use ratio or root. So absolute or alternating series cannot show absolute. Okay, go fill in. Let's see which bullets you get to fill in for essential questions. 1, 2, and 4. So go fill in 1, 2, and 4 from your essential questions.